Thanks. And I'd like to thank the organisers for inviting me here. Now, you're going to have a couple of problems with this talk. One will be the Australian accent, which I can't do anything about. And another is that I'm a mathematician, not a physicist, and so there will be some culture gaps, but we'll try and deal with that. So there are a number of areas, a number of problems that arise from quantum computing that have overlap graph theory, and quantum walks is one of them. And so today I'm talking about some work on continuous quantum walks. So I'm going to start by going over some background, most of which is sort of completely trivial, but it may at least get you used to the notation I'm using. One thing I should say is that, okay, I'm talking about open problems, questions that I would like to solve or see solved. And to provide motivation, I'm going to talk about some of the work we've been doing. And the work has been, by and large, with this group of people, so of which Harmony Hanmeng is here. So, you know, it's joint work, and I'll try and be accurate, but we'll see how we go. From my point of view, the stuff that I'm talking about starts with these three papers. So these are standard. I don't think anybody's any surprise. And so, you know, everything's built from this, from those papers. I'm a graph theorist, and so my interest, continuous quantum walk is a walk on a graph. And so what I'm interested in is the relation between the properties of the walk and the properties of the graph. I might hope that by seeing if I get some unusual property in the walk, it tells me something interesting about the graph. So I'm going backwards and forwards between the graphs and the physics, if you like. But let's just write down a few things just to fix notation. So I'm going to have a graph X, which is perhaps not standard, and it's got an adjacency matrix, which is the 0, 1 matrix, symmetric, and with zeros then a diagonal. The Laplacian will come up later on, but I'll generally be using the adjacency matrix. And if we have an initial state given by a density matrix, the state of the system at time t will be given by that expression there. So this is describing a quantum walk. D is the initial state, the state of time t is given. And so that's the framework that we're working in. Usually the initial state, I tend to write it in terms of vectors, but you guys prefer bras and kets, so I've done both just to prove I'm bilingual. So usually the initial state would be of a simple form, and you're carrying out your measurements at time t in the standard basis. Now you have other choices, but this is common and covers many of the situations you're dealing with. Okay. Now don't think anybody here is in doubt about any of this, but this is just my notation. And of course I've got my Schrödinger's equation going backwards in time, but that doesn't matter. Yeah, come on. So for a continuous quantum walk with transition matrix U of t, well, the entries of U of t have got phase factors in there. If you carry out a measurement, then all the information you get is contained in what I call the mixing matrix, which is the Schur product of U of t with its complex conjugates. In other words, to get m of t from U of t, I just take the square of the absolute value of each entry of U. So this is a well-defined matrix. It's got the advantage of being real. The entries are non-negative because they're squares of absolute values. Each row sums to 1 because U is unitary. Each column sums to 1. It's symmetric because U of t is symmetric because the adjacency matrix is symmetric. And so it's often more convenient to state questions in terms of the quantum walks in terms of the mixing matrix rather than the U of t itself. Anything you can measure experimentally is contained in the mixing matrix. Everything else is phase factors, which are not physical. Okay, so to give a very simple example, if I take my graph to be the complete graph on two vertices, then the matrix is very simple. And in this case, you can work out in more than one way what U of t is, and it's this mixture of cosines and sines. It's a unitary matrix. As I said before, it's symmetric. And there's the mixing matrix, and you see a new proof that cos squared plus sine squared is equal to 1, because each row is summed to 1. So that would be the mixing matrix. So that's the easiest possible case, although it's not trivial, as we'll see. Now, I'm interested in properties of the walks, and I can illustrate these properties on this already on K2. Okay, we look at what happens at various times. Okay, and I've distinguished three cases, pi and 4, pi and 2, and pi. Now, at time pi and 4, the entries of U all have the same absolute value. So the mixing matrix will be 1/2, 1/2, 1/2, 1/2. Okay, and that's referred to as uniform mixing. The case that people are most interested in is the second one, pi on 2. Well, m of t would be 0, 1, 1, 0. This corresponds to perfect state transfer. So, and the third one is simply if you go to time pi, then u is minus the identity, and so m of t is just the identity, so you're back to where you started, and this is what's called periodicity. Now, periodicity is not too much use in practice since you don't normally want to get back to your initial state, and there are cheaper ways of doing it than running the walk. But the issue is that if you have perfect state transfer between two vertices at time t, then you're guaranteed to have periodicity on each of those vertices at time 2t. So periodicity comes with perfect state transfer. And when you're trying to decide whether some graph admits perfect state transfer, it's generally easiest to first look for the periodic vertices and then test which ones of those work. So it's a useful tool. Okay. As I said, the main focus is one of the basic questions is simply if you've got a graph, is there perfect state transfer between two vertices on this graph? Okay, and that's in some sense what I'll be talking about for most of this talk. Now, at the moment we have one example of perfect state transfer, and it was easy, which is good, but it's just the K2, the graph on two vertices, and so if we really want to have a meaningful discussion, we'd like to know there are more examples. Okay, and so I'm going to provide these examples. Now, there's two ways of looking at this, and for the graph theorists, it depends on this construction. Now, this is a standard product of graphs, and I'll give you a picture in a moment, but the idea is that I'm going to construct a new graph from two input graphs. The vertices in the new graph are the ordered pairs of vertices from the graphs I started with. So now I've got these ordered pairs, so that's the Cartesian product of the vertex set. When are two ordered pairs going to be adjacent in the new graph? They're going to be adjacent if they agree on the first coordinate and the second coordinates are adjacent, or if they agree on the second coordinate and the first coordinates are adjacent. Now, you can think about that while I sort it out, but the best thing is just to stare at the picture. So this is the Cartesian product of P4 with itself. So when you draw the Cartesian product, you have vertical, of two graphs x and y, you have vertical copies of x and horizontal copies of y. So it's perfectly straightforward. It's a standard product in graph theory. The reason it's relevant, this is something that was noticed by Christandel in the original paper. If you're looking at the transition matrix for a Cartesian product, it's the tensor product of the transition matrix of the factors. So you could think of, on the left-hand side, you're thinking of a quantum walk on the Cartesian product. The right-hand side, you've just got two independent quantum walks on the factors. Okay, and so this means that very quickly you can get a bunch of examples. The standard example here is, well, I started with K2, that's the only graph I got, so I'm going to start taking Cartesian products of K2 with itself. I'll call that Cartesian powers. Okay, now the dth Cartesian power of K2 is just the d-dimensional hypercube. It's a exercise, but it's not hard, okay? And because of this relation here between the Cartesian product and the tensor product, you deduce that, well, you can certainly write the transition matrix for the d cube as a tensor power of the transition matrix for K2. And as an immediate consequence of this, that at times pi and 4, pi and 2, and pi, you get respectively uniform mixing, perfect state transfer, and periodicity on the d cube. So on the d cube, in particular, you get perfect state transfer between pairs of vertices at maximum distance, which would be d in this case. Okay. I'll say one thing, it's not altogether clear why the uniform mixing is occurring. In many of the examples, what happens if you do have perfect state transfer, that at half the perfect state transfer time, you get uniform mixing. Now, we have many examples of that. There are also situations where it doesn't occur, but we don't really know. We don't have any sort of nice natural explanation for it, but you know, it does happen. So the point would say uniform mixing, well, who cares? Well, you could say it's a nice way of generating a uniform distribution, but the other issue is that it does seem to go along with perfect state transfer in many cases. So it's worth keeping in mind. So the point there is to give you a bit of background and get used to looking at my notation. So now I want to go on to the questions that I'm interested in. Now, these are a bunch of open questions that have come from our work over the years, and I'm going to start with the perfect state transfer. Now, this is simple enough to state. If you have perfect state transfer at some time, and you write things out in projective form, that tells you U of t applied to the ket A is going to be a complex scalar times ket B. straightforward enough. And in all the examples we have of perfect state transfer, that phase factor is a root of unity. Gamma to the n is equal to identity for some n. Now, if I knew that was true, this would make life easier in a lot of calculations. But I don't know it's true. I can't prove it. So that's one reason I find it interesting. The other point is that we have a reasonable grasp of when perfect state transfer occurs, but in a certain sense you can say, well, we've got a couple of collections of methods. We've got this Cartesian power trick and a kind of quotienting trick, and so you get a bunch of perfect state transfer by using those two tricks. But in those cases, you're going to get the gamma as a root of unity. Now, the question is, are there more more varied ways of getting perfect state transfer? Now, if you do that, it can be a bit hard to decide, is this new or not? But what I'm saying is if you can find a perfect state transfer and that phase factor is not a root of unity, then it's different from anything we already have. So it's a fairly simple test, okay? And the third comment I should make here is, okay, we're talking about roots of unity, so this is bringing in number theory, which I know makes some physicists nervous. It's somewhat, well, from my point of view, it's interesting because working with quantum walks, the mathematics is a mixture of linear algebra and number theory. And actually, you get some fairly deep number theory at times, okay? And so this is a baby example. In this case, I'm just asking a question. Now, you can argue that perfect state transfer is unusual or rare, and the first theorem I'm quoting there is evidence in favour of that. So it says if you fix an integer k and you look for connector graphs where no vertex has more than k neighbours, then only finally many of those graphs admit perfect state transfer. So you know this is a saying. So it depends on the ordering, but you can view this as saying that perfect state transfer is not common. Okay. Now that's fine. I have a suspicion that something stronger is true. So I'm putting a restriction on the maximum valency of a vertex, and so the idea is, well, can I weaken that? So one way of weakening it would be say, instead of saying the maximum valency, so that of a vertex, I could say, provided the average valency is not too large. Okay. Now, the reason I'd want to prove that, the canonical example, if you have a tree, the average valency of a vertex is 2, and you can't get much more than that. Now, trees are interesting from the point of view of state transfer because they're networks and they've got the minimum possible number of edges to be connected. So questions about trees are of some interest. Okay, if you want to have a network, then trees are a good place to start. Now, the question simply is, we don't have any examples of a tree with more than 3 vertices where perfect state transfer occurs. The graph K2 is a tree, and the path on 3 vertices is a tree, and they both have perfect state transfer between their end vertices. Okay, but we have no tree bigger than that. And I suspect that there aren't any more, but I don't see any way of proving it. So I've got some more refined questions that might be a bit more accessible. But the situation is a little different when you come to Laplacian, but I'll come to that later. So instead of asking for the average degree, I could simply state the question in terms of the diameter, the maximum distance between 2 vertices in the graph. So we've got the path on 2 vertices has PST, that's got diameter 1. The path on 3 vertices has got diameter 2. What I'm saying is it's possible that if the diameter is large enough, you can't get PST. And it's possible that might be easier to prove. So I've raised it as a question. Now, the more general question would be, the big question would be to prove that if you have a positive real number C, there's only finitely many connected graphs with average valency in most C on which perfect state transfer occurs. Now, that's harder than the tree question, so this is the general question. And as I said, we've thought about trees for quite a long while and not made any real progress. So that's that. Now, when you're working with continuous quantum walks, I said I've been using the adjacency matrix, but there are a number of other matrices you could use, and one that's the most common alternative would be the Laplacian. And so I've just defined the Laplacian here. So I take my graph, I write down the diagonal matrix whose ith entry is the valency of the ith vertex, and the Laplacian then will be a diagonal matrix minus the adjacency matrix. Okay, and so then for the transition matrix, you replace your adjacency matrix by the Laplacian. Now, generally speaking, nothing changes qualitatively when you go from the Laplacian to the adjacency matrix. Okay, the Laplacian in some sense is more natural, because if you want to think of it as a quantum walk, as an analogue of a classical continuous walk, then the Laplacian is the right matrix. But in practice, it's not just me. People generally seem to work with adjacency matrix. And if you do calculations or you start looking at examples, you run through the graphs on 9 vertices and seeing what's happened, you discover that by and large, the data doesn't seem to change that much depending whether you use the Laplacian or the adjacency matrix. But there is one important difference. Coutinho and Liu proved that for a tree on at least 3 vertices, the continuous walk with the Laplacian Hamiltonian does not emit perfect state transfer. And it's a fairly short proof and quite elegant. And so it makes it doubly annoying that we can't decide what happens with the adjacency matrix. And as I said, there's by and large, the proportion of vertices graphs that have PST with Laplacian is not that much different from the proportion of graphs that have PST with the adjacency matrix. It's not clear mathematically that there's a huge difference, but there is this result. Liu was an undergraduate at the time when this was done. So that's it for perfect state transfer. Now, the natural question for a graph theorist to ask, well, if I'm going to have perfect state transfer, I've got these 2 vertices A and B, and I get my PST from A to B. Now I ask the question, well, what properties does that mean that A and B must share? I mean, if I want to find graphs of PST, the more restrictions I have on the possibilities, the easier it is to identify for which graphs it occurs, which graphs it doesn't. So, I mean, a simple question you could ask, if I have perfect state transfer from a vertex A to a vertex B, do they have the same valency? So this is going to lead to what I call co-spectrality, but we'll get to that in a second. This is a little calculation. What this is showing is if you have perfect state transfer from a vertex A to vertex B at time t, then at time t you would also get perfect state transfer from vertex B to vertex A. And so that means you run things for twice that time, you would get transfer from A to B back to A, so you'd have periodicity at the vertex A. And this is how periodicity and PST are related. Okay, so, and in fact, so the point is so the transition matrix is swapping ket A and ket B, and if I don't want the phase factors, I can suck them into the transition matrix, and so then I have a matrix, a unitary matrix, gamma inverse U of t, that's swapping ket A and ket B. Okay, so this is a consequence of the definition of perfect state transfer. It's a property of the 2 vertices. Now, what does this tell me? Graph theoretically, now in graph theory we have this, you can ask questions about the spectrum of the adjacency matrix, but here I've got a fixed graph and I've got 2 vertices A and B. I'm going to say those 2 vertices are co-spectral. Well, usually I would say that if the graph I get from X by deleting A has the same character polynomial as the graph I get from X by deleting B. So the graphs X drop A and X drop B are co-spectral. They have this, the adjacency matrices are similar. Now, because of the previous slide, I know that if I have perfect state transfer, then U of t, U of t is a polynomial in the adjacency matrix, so it commutes with A, and it sends A to B, and it's, not U of t, I should have gamma inverse U of t, and so it still does both those things, and gamma inverse U of t squared is the identity, and so this could be taken as a definition of co-spectrality. So the one way of thinking of it, which if I'm talking about graphs and similar vertices, I'd be thinking in terms of automorphisms, which would be permutation matrices. And so you might look for an automorphism which maps vertex A to vertex B. That would be a permutation matrix which sends A to B. So a graph theorist is using permutation matrices. But for a physicist, you're thinking in terms of Hamiltonians, and you're thinking of symmetries of the Hamiltonian, and you only require those to be unitary or orthogonal. Okay, and so in a sense, this Q of t is giving you the symmetry, but this corresponds exactly to this graph theory notion of co-spectral, and so the conclusion then is that, well, this is a good, actually, yeah, distract myself here. So it's easy enough to construct cospectral vertices. You take two copies of a graph and join the same vertex in each copy, and then the vertices you join are cospectral. So whenever there's a symmetry in the graph swapping two vertices, those two vertices are cospectral. One of the things this example here shows is you can get cospectral vertices where there's no symmetry in sight. There's no graph theory symmetry. Now, in terms of, if I go back to the more general definition I was giving in terms of the Qs, there is an orthogonal matrix which swaps ket U and ket V and does all the other nice things. So, cospectrality is a little strange. The other point is it's, reasonably straightforward for graph theorists. If you know the vertices are cospectral, they will have the same valency and a bunch of other properties. Okay. So cospectral vertices occur. They're not always occurring in places that you expect to see it. And so the point then is that if I have perfect state transfer, then the vertices involved are cospectral in the sense I just described. Now it turns out that's not the full story because in that example I just gave you with that tree there, those two vertices are cospectral, but they won't have perfect state transfer. But the other point is that having PST gives you something a bit stronger than being cospectral. And so I've written up another definition. Actually, I haven't got to it yet. Let's go back a second. Yeah, okay, I see what the problem is. What I want to do is define strongly cospectral, like in the title of the slide there. Okay, so this is a strengthening notion of cospectral, and so I've left out strongly in the top first line of the definition there. So strongly cospectral, the first three conditions are the same as I had on the definition of cospectral, but now I've added a fourth condition. I want Q to be a polynomial adjacency matrix. Now that's something I get when it's perfect state transfer because, as I said, U of T is a polynomial adjacency matrix. So, it's interesting, graph theorists, we worked with cospectral vertices. I mean, I showed you that tree that Schwenk used back in 1973. Now, that was long before people were thinking about quantum computing. So we were thinking about cospectral vertices. But what happens when you look at quantum walks, there's something stronger relation. We get this strongly cospectral. So there's a sharpening, which is not something I would have come across graph theoretically. But by thinking about these walks, I get this new relation. And the upshot is that vertices that are related by perfect state transfer must be strongly cospectral. Now, to answer the obvious question before you ask it, that's not enough. It doesn't force PST. I threatened before that in this area of the mathematics, you need linear algebra and number theory, and being strongly cospectral is purely a linear algebra condition. Okay, so it's not enough. Okay. In terms of examples, it is true that if you have a graph and the eigenvalues are all simple and two vertices are cospectral, then they're strongly cospectral. So that tree I drew with the two vertices U and V, they would be strongly cospectral. And you'll see another example in a moment. So here's a construction I referred to before. I'm taking two copies of the same graph and then joining corresponding edge in each, corresponding vertices in each. So I've used A and B here to avoid some confusion, but I picked the same vertex in copy of X and joined them by an edge. That's a graph. Okay, simple enough. And you can show that if those two vertices A and B there will be strongly cospectral. So this is a simple way of getting strongly cospectral vertices. And so now you have the innocent question, is there a connector graph where X has more than one vertex of that form, and you do get perfect state transfer between those vertices? Now, as I said, the problem becomes, when you come to work it out, involves number theory. I have to make X have at least one vertex, because otherwise I might just get K2, which does have perfect state transfer. But the question is, can I use any bigger graph? Now, it's a fairly simple situation. And you can sit there and do computations and stuff, but I don't have any real idea and any nice, really nice examples. Leave that. Okay. So I want to lead up to if perfect state transfer is rare, you might start thinking about, well, maybe there's some relaxations which are still useful, and I'm leading up to that. But I'm also giving you a somewhat different viewpoint, which I find very useful. So I'm going to work with density matrices. and I'm going to have I've got my quantum walk U of t given by some graph. And now I'm going to look at all the matrices U of t for t and r. Now that set of matrices is a group. It is a subgroup of the unitary group. Okay, and so when you look at the set ut d sub a u of minus t, that's all the density matrix you can get by applying in your quantum walk. So that's the total image of the quantum, everything that can appear on the quantum walk. Now that's an orbit. So you've got a Lie group acting on something. So you're in a very controlled situation. And now, if you think about these terms, so for each density matrix d sub a, I've got an orbit. I get PST from A to B if the orbit of d sub a contains d sub b. So it's in that sort of a geometric point of view, it's a very simple condition. You say, is this in the orbit of that point? If it is, you've got perfect state transfer. If it's not, you don't. That's simple enough. So perfect state transfer is in the same orbit. So the generalization is more than one name. I call it pretty good state transfer. I'm saying I have pretty good state transfer from A to B if d sub b lies in the closure of the orbit. Now the issue here is that in a fairly simple case, you can think of the orbits as sitting on the torus, and you'll see pictures on the torus of curves that go around and are dense. And so that orbit can look like that. Okay, if you're familiar with Lie groups, this is all triviality, but the statement is that if D is in the closure of the orbit, then you're getting what we call pretty good state transfer. Now you can express this in simpler terms, and it simply says that you pick your epsilon positive, there's a time t such that u of t d sub a u of minus t is within epsilon of d sub b. So you're getting approximate or pretty good perfect state transfer. I can't get perfect, but I can do pretty good. Okay. Now this is it's a natural enough generalization that's occurred to a number of people. I won't go into that. I just want to give you one result which gives you some idea of the complexity, and you'll see some of the number theory coming in. A group of us proved we're looking at pretty good state transfer between the n vertices of a path. Now for perfect state transfer, you get PST between the n vertices of path on 2 vertices and the path on 3 vertices, and no more. And it's not spectacularly difficult to prove, but it's not trivial. It takes several pages. For pretty good state transfer, the situation is a lot more complicated. I have a path on n vertices, and I'm asking for PGST between those n vertices, then it occurs if only if one of those 3 conditions hold. Number of vertices plus 1 is a power of 2. Number of vertices plus 1 is a prime. Number of vertices plus 1 is twice a prime. Now this is purely a number theory condition. Okay, and physically it's quite weird because it's a little hard to imagine a system where the behaviour is going to depend on whether you're dealing with a prime or not. But I mean, this is what happens. Okay, now these results have been extended, but the issue is, okay, it does occur. The problem physically is that you may have to wait a long while for it to happen, but I won't go into that now. But what I'm saying is you do get PGST, but it depends on number theory. And I said that, so I'll go on. And so now I can ask another question, for which connected graphs do I get pretty good state transfer between those 2 base vertices? Now, this you can. I didn't draw the picture. If you take the star, one vertex with m neighbours, and use that for x, then if 4m plus 1 is a perfect square, you get PGST, and if it's not a perfect square, you don't. So again, it's a number theory, but it's interesting. The previous conditions were divisibility conditions and primes. This is it depends on whether something is a square or not, so it's a different flavour of number theory, but it's still number theory. So that mathematically this is quite surprising. The other point is, well, I mentioned Gabriel's name before, and he's in the computer science department, so he asked the question, is it possible to determine in polynomial time whether a graph admits pretty good state transfer? Now we can, he and I showed that you can, if you give us a graph, then in polynomial time you can decide if there's PST between 2 vertices or not. Okay, we don't know whether you can get, how hard it is to determine PGST. I think Gabriel has a hope that you can do it in polynomial time, but I'm more sceptical. the issue is with the PST, the results would tell us if it's going to occur, it must occur within we have a strict upper bound on the time. And so in a certain sense, that narrows things down. But for the PGST, we have no idea at this point. Okay, so, excuse me. The next topic is what I'm going to call averaging. Now, one way of motivating this for me is that if I construct some natural parameter or natural matrix depending on the quantum walk, then I've got a graph invariance. I've got a new property of a graph. And so I can ask questions about the relation between properties of the graph and properties of this invariant. Okay, so the invariant I'm going to introduce now is what I call the average mixing matrix. So remember that the mixing matrix entries are just the squares of the absolute values, the entries of the transition matrix. Okay, so it's a non-negative matrix with rows and columns summing to 1. And I'm going to define the average mixing matrix the way I've just done it up there. Or you can dig out more from references from that. Now, the 2 comments. The first thing is that averages like this appear, well, in ergodic theory, in particular in work of von Neumann. And it's always nice to be able to cite von Neumann when you're trying to talk to physicists. But so, not exactly this one, but something very similar. Now, of course, the other question is, any fool can write down a limit like this, but does it exist? So we can take care of that because we can compute it another way, and it gives us more information. So I got my adjacency matrix, A, it's been there all along, and now it's got a spectral decomposition. Okay. And so the eigenvalues are theta r, and the idempotence, the projections in the eigenspace are E sub r. So the U of t has a spectral decomposition. It's got the same idempotence, and the eigenvalues are e to the I t theta r now. Okay, so we can write out that we've got the spectral decomposition for U of t. And so now I can write out a formula for M of t. And so I get something which looks like a spectral decomposition, although it's not. But it's still a linear combination. I've got things like, I got e to the it theta r minus theta s, this scalar one linear combination, and it's a linear combination of matrices. These matrices are the Schur products of ER with ES. So this is the bad student's product of 2 matrices. You multiply the ij entry with the ij entry. So that's all I'm doing there. So I'm just using linearity, I get to this. Now, this is a Schur product of 2 positive semi-definite matrices. And so, for example, there's a theorem of Schur that says that product matrix is always positive semi-definite. Not that that really matters. Now, the point is I don't really care at the moment about M of t. I was interested in this average. When you do the averaging at simple calculus, the off-diagonal terms all go away. And so the average mixing matrix is just the sum of the Schur squares of the idempotence. Okay, which is a perfectly reasonable concept, but nobody thought about looking at this before started looking at questions about quantum walks. Now, let's do a very simple example. If you take the complete graph on n vertices, then it's adjacent. Well, I use graph theorists, and we'll use J, uppercase J, for the all 1 to matrix. In this case, square. So the adjacency matrix of the complete graph is just J minus the identity. Okay, and you can work out very quickly that the idempotence in the spectral decomposition of the adjacency matrix, the complete graph, are 1 on n times the all 1 to matrix, and the identity minus 1 on n times the all 1 to matrix, because there are only 2 eigenvalues, and the idempotence have to sum to the identity. And so once you work out the first idempotent, you've got the second. And so therefore, with a little bit of work, you get the expression for the average mixing matrix for the complete graph. Okay, so it's a 1 minus 2 on n times I plus 1 on n squared times j, which has got a somewhat surprising consequence. So for a large complete graph, that average mixing matrix is pretty much the identity. Now that's a little weird already, but it leads to something even stranger, which we'll see in a little while. The average mixing matrix does have a number of special properties. The Schur square of a positive semi-definite matrix is positive semi-definite, and so M hat is a sum of positive semi-definite matrices, so it's a positive semi-definite. If that's straightforward physics, I guess you would call them positive rather than positive semi-definite. The entries of that matrix are rational, which is not obvious. And the other comment I'll make is that two rows of the average mixing matrix are equal, if and if the corresponding vertices are strongly co-spectral, so all these things are tying together. So it's a useful matrix. You can show that if the rank of that matrix is 1, then the graph must have at most 2 vertices. And a bunch of us spent a lot of effort looking at the case of what happens in rank 2. And the question is whether infinitely many graphs where the average mixing matrix has rank 2. I don't have a clue. I guess it's a short answer. But so it's a fairly strong restriction, what I would have thought. But we have a number of examples, just enough to make it complicated. But I want to go back to another property of the average mixing matrix. I said the fact that the average mixing matrix for the complete graph was close to identity was weird, and I want to drive this home. It's not too hard to prove from definition that I'm using the curly greater than or equals to denote that the difference of the two sides is positive. So I'm saying that I minus the mixing matrix is positive semi-definite. And M of t minus twice m hat minus I is positive semi-definite. And now for the complete graph, this yields that the M of t minus this stuff here is positive semi-definite. Now that means that the diagonal entries, if A is curly brackets greater than or equal to B, then the diagonal entries of A must be greater than or equal to the diagonal entries of B. This is a fact about positive matrices. So this statement here tells us that the diagonal entries of M of t are bounded below by this. So I said that M hat was close to identity, but now I'm saying a lot stronger. Now I'm saying M of t is close to the identity. And this is kind of bizarre. It says if you do a quantum walk on the complete graph, and you measure at some time t, with very high probability you're on the vertex you started at. Okay. So I'll say a family of graphs is sedentary if there's a constant c such that this happens. And so given that definition, follows from what's up here that the complete graphs are sedentary. Now, I have many other examples. The issue is that by and large I need my graphs to have a relatively high valency, and so a concrete question is whether there's a sedentary family of connected cubic graphs where every vertex has got valency 3. So I've got some work on this. I can give you examples other than complete graphs, so there are examples of sedentary graphs. And one feature, as I said, is that generally for those graphs, those families, the valency is increasing with n. So the question is whether you can do what you can do in a constant valency case. Okay, not good. So my final group of questions is related. I was talking about way back on one of the first slides about uniform mixing. So the uniform mixing occurs if there's a time t such that all entries of u of t have the same absolute value. Okay, and there's a variant of this that you can ask for that. You might also say, well, there might be situations where if I start at a certain vertex and measure at a time t, that all outputs are equal likely. That would be saying that a certain row of the mixing matrix had all entries equal. That'd be 1 over n. So that would be local uniform mixing. So we've got these two variants of uniform mixing and local uniform mixing. And so if you have local uniform mix at each vertex at the same time, you have uniform mixing. Right, so now there's a long slide here giving you a summary of what we know about it. I showed you earlier that the complete graph or path on two vertices emits uniform mixing at time pi and 4. And so the hypercube also emits uniform mixing at time pi and 4. And as I mentioned before, there are many cases where we have, if we have PST at time t, then we have uniform mixing at time t on 2, and we don't really have an explanation for why this would happen. The complete bipartite graph, so this is K13, so you have one vertex joined to 3 others, no other edges. That graph emits uniform mixing, and the Cartesian powers work too. And this is the observation is due to harmony sun. And this is the only family of graphs which are not regular, where I know that we have uniform mixing. We do get local uniform mixing in other cases on the bottom there for K1n. if you're going to get uniform mixing, you expect the vertices of the graph, it's simplest when the vertices of the graphs are all similar. And the easy way to do that is when, for graph theorists, to say, let's assume that for any two vertices, there's a graph automorphism which takes one vertex to the other. This would be a so-called vertex transitive graph. Now, if you're looking for examples of vertex transitive graphs, the simplest examples, simplest not entirely trivial example will be the cycles. Okay, and now the only even cycle that admits uniform mixing is C4, and the only cycle of prime lengths that admits uniform mixing is the complete graph on three vertices, the triangle. It's somewhat annoying. It's unlikely that the odd cycles admit uniform mixing, but we don't have anything like a proof at this point. And so that's the first question. So which odd cycles admit uniform mixing? Now, Gabriel and Crystal said they looked at C9 and ruled that out. So probably the first open case is 15. Now the question would be, is there a graph other than K13 that is not regular and admits uniform mixing? And so a related question would be, which trees admit local uniform mixing? Now, to finish off, I just want to, so as I said, if I want to be, well, I want to state a couple of conjectures due to Natalie Mullen. If I'm looking for uniform mixing, it's natural to focus on graphs that are vertex transitive. And so what I'm doing here is giving you an infinite way of constructing vertex transitive graphs. So I want to do it, I construct what I call a Cuddy graph. And it's really fairly simple. You start, okay, I want to get I start with some group, a finite group normally, and I pick a subset of the elements which I'm calling script C. And so the vertices in my graph are going to be just the elements of the group. So I'm constructing a graph is vertices of the elements of some group. And now when I define a graph, I've got to tell you what the vertices are, and then I've got to give you the adjacency rule, a way of telling whether two vertices are adjacent. And so the rule is that little g will be adjacent to little h if hg inverse is in my set script C. Now, because I want to get a graph and not something slightly weirder, I want to assume that my set script C doesn't have the identity, and that if it contains an element C, it contains the inverse. But so anyway, so you choose it carefully, you get a graph, and these graphs are always vertex transitive. There are vertex transitive graphs you can't get in this way, but that's not going to matter. And well, the simplest example really is to take the cyclic group of order n and just take the elements 1 and minus 1, and then the graph you construct is just the n cycle, but we don't need another description of the n cycle. And so the former student Natalie Mullen's got two conjectures. And again, see, the first one's number theory. It says if a graph emits uniform mixing at time t, then e to the it is a root of unity. And the other thing she conjectures is that if n is greater than 5, then no connected Cuddy graph for zn to the d emits uniform mixing. So we do have uniform mixing on Cuddy graphs for z2 to the d and z3 to the d, and probably z4 to the d. Did we ever? I don't think we ever really got to that, but it's likely for z4 to the d. If the answer to the first question sort of helps you, it would be, if we knew this was true, then it would be a lot easier to decide the second question. That's probably the way of doing it. And thanks for your attention. That's the end of the talk.
So questions?
Oh, hi. You talked about uniform mixing and perfect state transfer. Recently, we wrote a paper about something quite opposite. We looked at zero transfer, which means during this quantum work, some nodes would be completely hidden.
Yeah.
The techniques you applied here, do you think it would apply to zero transfer?
Tino Tamon has done some work on this, and we've thought about it a little bit. We actually do have some results that, it's not my terminology. Tino says a vertex is evanescent if there's a time t at which that entry of the matrix is 0. And so we have a few results about more or less examples saying that in these cases there are. But it's fairly easy to write down examples where you do the plot and you're convinced that this will be 0 at these intervals, and we don't have a proof. So for example, to amuse yourself, you look at the cycle on 5 vertices. You do you're going to do transfer on that. Okay, so you work out U of t and you plot it. Now I want to look at the 1-2 entry of the cycle. Now it's a complex number, but it's only so. But I can plot it in the plane, and so I get a nice plot. It looks like a 5-leaf clover. When you let it fill out, it starts at 0, and I should have done it. But it starts at 0, but we don't know whether it's ever 0 again. So these questions are difficult. Yeah.
Thank you.
Yeah.
It's a pretty good
State transfer.
So, do you have some example to obtain the graph? The time can be estimated. There exists epsilon such that.
Essentially, what's driving it is Poincaré's recurrence theorem. Okay, which means now, I mean, I know people in statistical physics, cite this and quote it. I'm not sure what the average of the average working physics to Poincaré's theorem is, because the waiting time is very large. So for the path on 3 vertices, you're getting perfect state transfer, small multiple of pi. I'm not going to try and get the right number now. For the path on 4 vertices, you do get PGST between the end vertices. But yet to get with 1% accuracy, you have to wait something like 800 pi. So, and basically, the waiting time, this is cuts, due to cuts, the waiting time is going to be, you're going to pick an epsilon ball around as your target. Now, it's an epsilon ball on a high-dimensional torus. And so the waiting time is 1/e to the dimension. Now, this dimension is termed in numbing theory for the path on 4 vertices, which is 2. As you go up, it increases sort of half the length of the path. So your waiting time is getting very bad very quickly. So that's the bad news. Now, there's an interesting paper by Feeder, which we've been trying to Feeder and a few others, which we're trying to understand, which seems to say that if you can modify the graph a bit and speed things up. But he's writing as a physicist, and we don't quite follow the mathematics, and so I'm not going to make a precise statement. Yeah.
So, another question. Did you consider pretty good uniform mixing?
Yeah, we have. It's in Natalie Mullen's thesis. It's kind of, yes, so you can't get uniform mixing on the 5 cycle, but you can get uniform mixing with any degree of precision. Which is kind of interesting. So you could, because sometimes people think if they can do something to pretty arbitrary precision, I should be able to do it exactly. But for the 5 cycle, you do not get uniform mixing. Tino and his students proved that, but you can get pretty good approximation. Yeah. Yeah.
Do you have more questions?
I have a question one. It's related to those question. Is there some of the you roughly consider that the pretty good uniform mixing? Is you say that's a little bit consider. Is there some of the relationship in the classical case? Classical uniform, pretty good type uniform mixing of the graph in the expander graph, I think.
Sorry, I'm
that's some of the expander graph. And that's some of the uniform mix, pretty good uniform mixing.
The problem is in the classical case, you always get mixing. I mean, if you have a classical connector graph, the long-term state is uniform. Okay, all arcs are equally likely.
Yeah.
So classically, you always get uniform mixing. So it doesn't have to be an expander; it just has to be connected.
I see.
Yeah. Okay. The quantum case, you don't, which is why the quantum case is interesting.
Okay.
Yeah. Yeah.
More questions? If not, let's thank Chris again.